Welcome to the last module for this semester, where we will be learning all about analysis of variance, commonly referred to as ANOVA, which just breaks down the analysis of variance phrasing into a shorter way to say it. So this statistical technique is the next level of t-tests that we discussed from chapter 10 when we were learning about William Gossett and how he compared different techniques for understanding sampling differences for brewing the best beer for Guinness. So thinking about module 10 and how we've come to explore other hypothesis testing that looked into other differences between groups. This is relatively similar, but we're focused specifically on this generalizable technique on how we can determine if differences exist between the means of now 3 or more populations. So prior to this, we've talked mostly just about comparing 2 different samplings. So now we will be building on that and learning through this ANOVA type of framework, which we will start with a one-way ANOVA, where we will analyze the mean between different categorical variables. And we'll build upon this to the two-way ANOVA that looks at more than one factor and will test to understand the relationship between variables conducted with or without interaction. So we'll start with this one-way ANOVA, examining how the mean of a sample is influenced by one categorical variable. For example, we'll talk through this case study of how the average distance traveled per day by people who own a different kind of wheelchair. So depending on the wheelchair category, what is the average distance traveled per day? And then we'll extend this case study to the two-way ANOVA, which will look into 2 factors. And in this case study, it won't just be the type of wheelchair, it will also be the type of tire on that wheelchair. And we'll assess how does that change the average distance traveled by the user. And we'll use these two-way ANOVA tests that are conducted either with interaction between these 2 categorical variables and without. So this is just a primer of what we'll be getting into today, and wanting to just explain how it relates a little bit to what we've talked in the last few modules with this hypothesis testing, how we're trying to use probability and statistics to understand how different do samples relate to each other, and using our testing framework to say at what degree are these things different, so we can find some type of conclusion, or perhaps things aren't that different, and that's a conclusion in and of itself. So some assumptions of this ANOVA framework are pretty similar to what we've usually had to rely upon for the validity of these different approaches, specifically that our populations are normally distributed, because we'll be relying on the different distributions in order to understand the symmetry and the probability of seeing a value at least as extreme as the value we see. And the one-way ANOVA is actually based on the F distribution from the previous chapter. So we'll be using that again, because in this type of framing, we are assuming that the population standard deviations are unknown, but we assume them to be equal. And this will be how we set up the hypothesis. And lastly, that these samples are selected independently. So there isn't any type of dependence between the 2 different variables. So based off of that, now we're more familiar with how we can test if things are actually independent of each other with that chi-square test that we just learned last week. So these are just some assumptions that we need to establish in order to test the analysis of variance between different groups. Any questions so far?
Yes. So back to the 1 versus 2 way. A one-way test would be just testing the wheelchairs for speed, and then two-way test be testing the wheelchair and the tires for speed, you said.
Exactly.
So just adding an extra variable onto it.
Yes, and this is where I think things really get interesting. because now you could really apply this to a real world business problem. And when we say with interaction and without interaction, we can now test, is there more of an impact when the wheelchair and the tire is this specific combination, and see how that results compared to just seeing these two different categorical factors as independent things. We're going to start to look at what's this interaction between these two independent variables as it relates to, whatever we're trying to predict, in a sense of like, what's the distance that would likely be traveled by a user with this type of wheelchair and this type of tire.
So like if you, I don't know, you had I don't know wheelchair brands, but I don't know, a Toyota wheelchair with like Toyota tires, you want to see if they run better together rather than if you have a Toyota wheelchair with Honda tires.
Exactly.
Okay. I don't think Honda or Toyota makes tires, but you know what I mean.
Yes, definitely. And so these are some examples right here in this table, where this is almost like the contingency table, or those cross tab, where you see like for this category, this is like the value if we look at the different categories here. So I guess instead of Toyota and Honda, we have K001 and whether the tire is solid or air filled.
Okay.
But you're thinking exactly right when it comes to like categorical variables. We're not looking at continuous things like, average rainfall compared to like humidity value. We're looking just at categorical variables.
Cool.
Awesome. Any other thoughts before we move forward? But great input there. So as we start to test this framework and use it, we will have the same type of 1, 2, 3 step that we've been seeing on all of these null hypothesis significance testing slides, where we want to first just think like, what are we trying to identify here? Really define what's the problem we're solving. This would then relate to, are we trying to develop a 1 or 2-tailed test? And we want to establish a claim whenever we are thinking about this framework of how we test an assumption about how the world might work. So in this case, our relevant population parameters are the mean. And note that the alternative hypothesis does not require all the means to be different from one another. Even if only 2 means differ, we can reject the null hypothesis. So in this type of test, it's like zero-sum game. It's either they're all equal, or even if one of the means are not equal, then it would not pass the null hypothesis. So I will just go to the next slide and that'll make a little bit more sense. But if we had to frame this question of, are there differences between the mean different distance traveled between types of wheelchairs? We would want to set this up as saying the mean distance between category 1, category 2, category 3 of wheelchair types. All the means are equal. That would be our null hypothesis. And then we would run our experiment to see if the average distance traveled between the 3 category types are statistically significantly different from each other, where that would provide evidence for us to reject the null hypothesis. So as I just mentioned, it doesn't matter if the category of 1 and 2 are equal, but if category 2 and 3 are not equal, this is a zero-sum game here. So it doesn't matter that 1 and 2 are equal. It would provide evidence to reject the null hypothesis. So when we're comparing these 3 means, we're not conducting numerous pairwise comparisons. We're simultaneously evaluating the equality of several means at the same time. So based on the null hypothesis in our example, we would expect the resulting means to be relatively close to one another. And to demonstrate what I just said a little bit more visually, we're really looking into the variability in the sample means and examining if the difference in this mean value can simply be explained by chance. So when we see this distribution and what it might look like if the null hypothesis was true, right here on the left, where the sample means are close enough together where there isn't really a statistically significant difference between these three different samples, compared to what we see on the right hand if the sample means would look if we were to have evidence to reject the null hypothesis, where we start to see these distinguishable three distributions that are resulting in statistically significant different means. And the reason this matters is that we can conclude that the variability in the sample means cannot be explained by pure chance alone. And therefore, there is a significant difference between the groups. So going back to like the wheelchair example, is there just by chance that the users in this experiment of one category of wheelchair traveled different distances? Or is it really because of the wheelchair type where perhaps there's some type of benefit or feature functionality in one of the wheelchair types that actually would result in a difference in the mean distance traveled? So we use this type of testing to really understand, are things similar or are they statistically significantly different? And I want to talk a little bit just about the origins of ANOVA. And because I think it's kind of interesting how a lot of this is based in agricultural experiments. Specifically in this case, now we're talking about potatoes, where different fertilizers were treated to the different plots of soil. And this was developed by Ronald Fisher, who pioneered principles of design of experiments, particularly of small samples and real data. So on the right, you'll see a table of different yields of patches growing the same variety of potato and investigating the differences or correlation between classes. Ronald Fisher analyzed the variance and symmetry of the distributions. And outside of developing ANOVA, Fisher promoted methods of maximum likelihood and inference. One other thing that should actually be mentioned about Fisher, because it's important to just have a full picture on some of these historic figures that we bring up in class, is that he actually held a very strong view on race and eugenics, insisting on racial differences, actually. So he taught eugenics at the University College London and is known as one of the three principal founders of population genetics. So taking this from potatoes and applying it on other topics, I think is just interesting to talk about here. So definitely would encourage you to look more into some of these figures that we are relying on what they established still, though, in statistics. But getting to how we will calculate this type of test, first, we want to determine if significant differences exist between some of the population means. We will start to develop if there's independent estimates of the variance between the sample means, and then if there's variance of observations within each sample. And lastly, we'll have this weighted sum of squared differences between the sample means and the population means, so sum of squares. So I'm going to talk through a little bit more right now of what this actually means when we are talking about the difference between, within, and how this all relates. So we develop two independent estimates of the population variance. So we're trying to understand how much variance exists in the population that we are looking at. So one of these estimates is referred to as the between treatments variance, and the other estimate is referred to as within treatment variance. And this is the population variance that is a measure of variability within each sample or the variability due to mere chance. So if the two independent estimates are relatively close together, then it's likely that the variability of the sample means can be explained by pure chance. And we would fail to reject the null hypothesis that the population means are equal. So this is when we're looking at the within treatment, or the variance within the groups. And if the between treatment variance is significantly greater than the within treatment variance, then this null hypothesis can be rejected. And we could think of this as being able to conclude that the ratio of differences between the groups is significantly greater than the variance within the groups. And bringing that to a more concrete example, we're trying to understand if the variance between 3 different samples are explained by the variance within these groups, or is there something else going on here? So we'll walk through an example that demonstrates how we would start to test these differences. But really the key points here are that we will test if there is a significant difference between different population means based off of the variance that just exists between the sample means and then the variability within each sample. So perhaps before showing that slide, talking about this slide, because we're on the right, we're seeing how much do these means vary from each other, but then how much within each of these samples do the observations vary. And I want to stop here for questions, just so we're, we can further discuss this type of concept.
Going back to the significance side, I mean the testing slide.
Or this one?
Not that one. No, not that one. The other one that we had. Yeah, that one, I think.
Okay.
How to calculate. You were saying something here, and I was writing stuff down, and I didn't hear you, so I missed it. I'm sorry. You said for the development of the estimates. What exactly does that mean again?
So we want to use, probability and define a statistic from the distribution that we see from our experiment. Mm-hmm. And this estimate is a calculation to define how much variance exists just between the sample means. That's bullet A. And then how much variance exists within each sample. And so that's why I brought up this visual again, because on the left, we see these 3 means are somewhat close together. And just if you were to look at this, you might say, hey, there is no statistically significant difference between these 3 means compared just for explanation purposes. If these 3 means were super far apart and we saw almost like an outlier in one of these wheelchair types, we might just be able to infer like, hey, these means are definitely not similar. Let's say we had one sample where it was like an electronic wheelchair compared to just non-electronic. So we would expect to see like a statistically significant difference in the mean mileage a user would be able to travel if there was an electric assistance compared to manual. So that is how we're seeing how are the means different from each other. That's bullet point A. And then the second one where we would start to see that on this right-hand side, we're starting to look at within each of those different groups, how much variance exists, because that would give us more insight where maybe if there's so much variance in that sample, then it could just be by pure chance that the mean is so different. So just for example, maybe the wheelchair category just has so much variance in how a user might experience it. Some days it's really effective and other days they have a lot of issues with it. There might not be kind of a consistent mean, and we might see a mean value that is so different than the other means just due to this chance of variance in how the wheelchair functions.
Okay.
So these are these 2 different test statistics that we calculate, because all we really have is probability and how often these things occur in our sample to depend on in order to evaluate, is there a significant difference between these means?
So a significant difference would be something more than, I'm assuming, 1 or 2, something that makes the line far apart, like the other one, like in B rather than A.
If what I'm hearing, are you talking more about, how statistically significant is it? Like, does it pass the
Yeah.
95% threshold, or like a
Yeah.
5%? Yes, exactly. So that's exactly how this relates to our hypothesis testing framework, where we want to make sure that we are finding evidence that is, extreme enough where it's not just, these things are kind of close to each other, where we don't even see anything like statistically significant about it.
Now, if we would graph it just to make sure that we're right.
I think graphing the role of that usually starts when you're exploring a problem rather than validating at the end of the problem. But that is perhaps my own approach, where when I'm faced with a problem and I just have uncertainty of what is actually going on here, I usually just start by visualizing it and graphing it. And that gives me a better impression of what I might expect. And then, testing my expectations based off what I see. So even thinking about this type of experiment, if you were trying to see how different potato fertilizers would result in different yields, I would start with plotting it and then starting to test how there are differences, because you might plot these and they might all be very close to each other, and perhaps that would give you some type of bias to assume that, hey, there is no difference. So I think it's just a little careful if you're applying this in the real world. I think it's always good to start with visualizing your data just to establish your own expectations, and really you're creating your bias of what you expect to happen based off of what you see. But that's kind of your role as the scientist here to understand and make your own assumptions and then test it using our hypothesis framework.
Okay.
So of course you could do it at the end just to validate what you did and perhaps remove some of that bias at the beginning.
All right. Got it.
So I'd say in a short answer, the answer is there's never a bad time to visualize. It kind of depends on your approach and what the problem is that you're solving.
Like if you really, really need it, do it. But if not, then it's okay.
Yeah, I mean, I think for the purpose of this class, if you're not asked to visualize, you don't need to, but it never hurts. And it does show like this next level of analyzing what you're seeing. And specifically, I think when visualization is most important is when you need to communicate these findings with non-technical stakeholders, where most often I find that when you visualize something, you can really better get the feedback you need based off of what you're showing. So if you were to take this type of experiment and, present it to your manager, I would suggest having visuals to demonstrate what you found.
Okay, that makes sense. Because then they'll just be looking at numbers, like, what is this?
And it just helps with how the kind of the influence, like the impact, when you see something on a chart compared to numbers, it really helps to drive your point home, perhaps stronger than a number on its own could. But perhaps this is getting a little bit out of statistics, but more so just like how to effectively communicate through numbers, which still relates to statistics. So, but
Yeah.
these are great questions.
You mentioned removing bias. Is there a certain formula we're supposed to run in order to do that?
So when I say removing your bias, I don't think there is always bias, depending on whoever is creating the experiment. And that's even why I brought up, Ronald Fisher's background of like how he got into eugenics, which I think is just, he's thinking about how do differences between like populations differ. And like, so his bias of how perceiving societal differences, like that's a huge bias. And he inflicted that on his, experiments in general. So, but I think I just say that because it's hard to actually remove any bias from what the experimenter would create, partially because you are creating the experiment, you're designing it, you're creating the performance metrics of how you're evaluating this experiment, and you're interpreting your experiment. So that's why it's important perhaps to overcome this bias, is to make sure your research is reproducible and making sure there are other contributors, even just to validate your approach, and they understand your assumptions you make. So I think the best way to fight against bias is really just to define it and communicate, this is my assumption, and therefore this is my rationale, so that someone else could, conduct something similar and understand this is where you were coming from. But even I think on a more technical sense, when we were to get into more modeling, if we wanted to remove some of our bias, there are definitely techniques to remove that when we would get into how we would develop a model of this. But that's outside of the scope of our class. But even just to touch upon that, like if you were creating an experiment, you want to make sure it's generalizable on new data. So you would want to frame your experiment in a way that doesn't employ too much of your bias, because your bias might be limiting the ability of the model to perform on unseen data.
Okay, thanks. I wanted to make sure I wasn't missing a step in the process, but that's really helpful. Thank you.
Yeah, there's no good step to remove bias is a shorter answer. Any other questions before we talk through another case study? Alrighty. So let's say you are a manager of a store and you think that if you were to change the layout of the store, that you might see larger sales as a result of it. So this might relate to having like end caps on your aisles, or perhaps smaller purchases near the checkout line, which usually I know a lot of grocery stores, that's where they make the most of their money, is just at the checkout line. So this is just a case study. If you were to change the layout of your store and sample 10 different stores for 1 month and calculate the total sales, you could use something like ANOVA to actually test if there was a statistically significant difference in the monthly sales based off of the categorical difference in store layout. So this is just visualizing the case study we'll be going into, where I created the distributions of monthly sales. And we can start to just see, kind of getting back, Darren, to your question, where my first step instinctually is to visualize things, where I would start to understand, okay, layout 1 seems somewhat close to layout 2, and then layout 3 seems a little bit more different, or even, I guess, because this is the textbook type of question, layout 1 looks very normally distributed compared to the other 2. So it's good, I would say, if I can define how I would approach something, is usually visualize it first, because this gives you just a good understanding of expectations of what you would start to analyze once we test something. So let's talk through how we would calculate this, where first we would define this between group estimate of the variance. And how we actually do this is, and this is all outlined in the textbook, and I'm just walking through it now, of step by step, where below you see some of those steps in mathematical terms, where first we add all observations and divide by the total number of observations. Next, we take the square difference between the sample mean of the group and the grand mean, which is the total mean. And we'll walk through this further. So for now, just it's good to have this understanding of what we're doing. But when you get to the homework, I would refer back to these types of steps because it really is kind of this methodical approach that we can take. And step 3, we would multiply step 2 by the sample size for each group. And then lastly, we divide by the degrees of freedom, which would be the number of categories that we are breaking this problem into. So for the wheelchair one, we had 3 categories, so we would subtract 1 from that. And so below you see the different formulas that we would look at. So that first step of add all observations and divide by the total number of observations, you see that here, if you see my mouse, where we divided by 30. And this is that grand mean. So like that X bar with another bar on top of it is that grand mean. And then in step 2, we're now taking the square difference between the sample mean, where we just have X bar, minus the grand mean. And we square that here. So this is very similar to whenever we're trying to find how much does something deviate from the expected value. Here's that formula again, where we have this square difference. And this is a consistent, even actually it's related to like a loss function. If we wanted to get into more kind of advanced statistical things, like this same exact formula is used in a lot of statistics of this squared difference. So we're seeing like how much does this mean vary from the grand mean of the observations. And then we multiply by the sample size for each group and divide by the degrees of freedom. And just to bring this back to what we were talking about, this is that first, the variability between sample means, where we're trying to calculate how far apart are these means just from each other. So that's why we are taking the mean of the total group and subtracting each group from that grand mean. So we're trying to see like how far are these means just from each other. And that's this component A.
So just a clarification on the numbers that you're using. So this looks like it's maybe 3 stores with 10 samples at each store.
Yes, let me make sure I clarify. Yes, it is 10 samples at the 3 different stores.
Okay.
And we'll walk through this in Python. So we'll have the actual numbers to play around with. Any other questions?
Just to clarify, this is how we're going to do the problems on Python, or at least for this part.
So this is how you would do this by hand, even.
Oh no.
Like just by paper. You know, that's why I have the formulas here below. You know, you could just take a calculator and do this yourself. So we'll walk through how we would do that in Python using just like math in Python, but then I will show you a function that does this all for you.
Cool.
Yeah, if that was your question.
Yes.
Okay, great. So this is establishing the between group variance of how these things differ. And this is just describing that a little bit further. So if the averages of all 3 groups are not so different, the variance among the groups, or the variance for the 3 average values, would also be very small. You know, if we're not seeing a huge difference in the means, this might also mean that there isn't a lot of variance between the 3, you know, categories of, you know, store layout in this example. But that's why next we look into how much variance exists within the group. So for each layout, how varied are the store sales? So we will test now the difference between groups and see if this is due to chance just driven by the natural variance that exists within that group. And this is how we would calculate that within group estimate of the variance using this, this sum of squares error and the mean squared error. And these are, again, these are like loss functions that are used for a lot of different statistical types of tests. And we're using it to understand what is this weighted sum of the sample variance for each group and seeing how this varies between the different groups. So we take this sum of squared error, which you have this formula right here of SSE, where we are, for each observation, taking this sum of variance for each group. And then we have this sum of squared error, and we divide that by how many degrees of freedom exist. And that gets us this mean squared error. And this error sum of squares provides us a measure of the degree of variability that exists, even if all the population means are the same. And so we take this weighted sum of the sample variance of each group. And that's how we then divide it by the degrees of freedom to just understand kind of the complexity that we're dealing with here, in order to just define this test statistic to simply just give us a measure of how much variance exists within the group.
So where does the sum of variance come from? Is that the sample mean minus the, where did that 0973 come from?
Yes, so we would calculate the variance of the sample. So from those 10 samples of the store layout, for each of these distributions, we would just take the sample variance of monthly sales, and that's what we would use. And that would be what that value of 0.0973 comes from. That is the sample variance of that group. Does that make sense?
Yeah, I need to figure out where, I think through an example, it'll come clear.
Okay, perfect. So that is what we'll be doing next, once we just finish talking about all the different inputs. So in one more slide, then we'll get to the demo of where we'll walk through it and where these numbers come into play. So for now, it's just walking through the general approach. Because with these different things we've talked about, now we can calculate this ratio of the variance between groups and then within groups. And this ratio is the test statistic for a one-way ANOVA test. And this is what we would end up using to be able to test our hypothesis and say, based on this statistic we calculated of how much variance exists just between the groups, and then within the group, we divide these by each other. And then if this value from the F distribution using our two different degrees of freedom from the numerator and denominator, we can now say with some degree of certainty that this value is very, it is evidence to reject the null hypothesis based off of our significance threshold we would establish. So this is just bringing it all together into how we would use this for our hypothesis testing. So next we'll walk through the example of how we would go by this step by step, but just bringing it all together, if we were to now wanting to test, are there differences between the mean monthly sales between the 3 store layouts? Our null hypothesis is that there is no difference in monthly sales. You can change the store layout, but you won't see any difference. And then we would conduct our sampling and create some data for us to experiment on, and then test, is there any statistically significant difference in the mean monthly sales based off of these 3 categorical variables? So let's jump to the demo, and we can talk through that a little bit more step by step. So we have some new packages here because we'll start to use some more of Python's built out functions, such as this pairwise. We'll get into this as we get into the two-way analysis, but for now, it's good just to start looking at what you do recognize. And I see some redundancy here, so we don't need that. But for now, you should be very familiar with some of these functions that well, function's not the right word, some of these packages that we've worked with before, such as stats, but also just start to see that there are some new ones here, like this stats models and this OLS, which we'll get into. But for now, let's walk through this example. And I just added some other helpful links where some of this code might be based off of as well for how we would solve these problems. So we want to conduct a hypothesis test at the 5% significance level to see if the average monthly sales are different between the store layouts. So this 5% significance level is somewhat of just a custom value of saying, hey, this is significant enough. But depending again on the experiment, you might need a higher significance level. But usually 5% is kind of a baseline. So we would establish this alpha for our hypothesis and establish our assumptions for the null hypothesis and the alternative hypothesis. Any questions so far before we move forward?
Yes, can you just walk us through how you assessed which null hypothesis and alternative hypothesis to use?
Yes, so going back to when we first introduced these concepts, when even just with that jelly bean example, where these 2 scientists wanted to claim that jelly beans prevent, acne from happening, we first need to just establish this null hypothesis that there is no relationship between acne and how many, jelly beans you consume. And then based off an experiment, they would need to find some type of evidence to say, hey, there is no relation, or there either is or there is no relationship. And so that would be this alternative hypothesis that you're trying to prove something exists there. Even bringing us back to the other example of innocent until proven guilty. This innocent is the null hypothesis, saying that there is no relationship between jelly beans or acne, and in this case there is no difference in monthly sales depending on how you change the store layout. And then what would make evidence to reject this null hypothesis is if we did see a difference in, acne levels as a result of jelly bean consumption, or as a result of this store layout, we did see a difference in the population means of the average monthly sale. So I think just a general rule for how to define these is the null hypothesis is what we would expect if there was no relationship between the variables. This is like the default state of how things usually would work. And then this alternative is what we're trying to essentially prove based off of whatever, experiment we're trying to test.
Okay, thanks. I think I'm more question specific here. So here it says conduct hypothesis test at the 5% significance level to see if the average monthly sales are different between the store layouts. And I'm wondering from that statement how you got null hypothesis U2 equals U1 equals U2, U3. Like, can you talk about that process?
Sure. And just to clarify, the U here is mu, the Greek letter
Okay.
that represents mean.
Yes, thanks.
And so I appreciate that we're talking just specifically here. And the way we would know how to structure these two hypotheses is because the question is telling us that we want to know if the means are different. So I knew that this was mean because we have the word average here. Perhaps if we were testing, variance, we would use variance instead of mean here. So I knew it was means because of that average, and we want to see if the averages are different. And therefore that would be our alternative. So we would assume that there is no difference because we're trying to test if there is a difference. So you kind of almost have to think backwards and maybe start with defining the alternative, because the alternative is what you're trying to find. So maybe just by reading this, we want to know that the average monthly sales are different. So therefore, that's what we're trying to experiment to find evidence to support. And that would be this alternative. So we're trying to, prove this candidate to be guilty of something. And then just think back a step of, okay, what would it take for this to be innocent, for there not to be any difference between the store layouts? And by default, that would mean that the means are equal, that because there is no difference.
Yeah, but the way this is stated to see if the average monthly sales are different, it almost seems like the null hypothesis here is that they are different, and that and then the alternative hypothesis would be that they're equal. So how did I get that mixed up?
Can you walk me through a little bit more of your thought process?
Just reading it, it seems like the statement is that they could be different. Like the person who's analyzing this is saying there's a possibility that they're different. So that seems like that would be the null hypothesis. Like we're testing if they're different, and on the off chance that they aren't different, that they're the same, that would be the alternative hypothesis. So equal or sameness would be the alternative.
Okay, I understand now what you're getting at, and it makes sense what you're saying and why you would interpret it that way. And I think it also extends to kind of the limitations of statistics and what we can actually test through this process. And we can really only test that the means are not equal, kind of different than saying that they are equal. Let me just bring up the slide just to talk through this a little bit more. I think this slide is a little bit easier to talk through, where we really only have the tools to test that these means are not equal to each other to a degree that is significant. We can't really do the opposite way of what you're saying, like would make more sense based off of the prompt to test that they're equal, just because of how the distribution, we're trying to see, are the differences different enough for us to find some type of evidence of something else going on here. Where if we needed to do the opposite of what you're suggesting of saying we need to prove that these means are equal to each other, we can't rely upon our same probability and statistics to say these are equal to each other, because they're never going to exactly be the same, just due to how things have variance naturally. But because of this natural variance and probability of the sampling and how we see the distribution, we can say that there is a statistically significant difference for us to assume that the null hypothesis can be rejected, that the means are equal. So in a shorter way, we're kind of restricted by the tools of statistics and probability in order to say these things are not equal to each other, but we really don't have the tools in this case to say that they are equal to each other. And that's why we have to define it this way, where this null hypothesis is what we're trying to prove against.
Okay, I think your innocent till proven guilty metaphor kind of is helping me understand that oftentimes the difference is the alternative. So we're hoping everything's equal, and then like the not, or that there's different becomes the alternative. Is that correct?
Yes. And so what I was just talking through was because of the distribution and the probability of seeing that mean. That's what we're trying to test to say this is different from this mean. And that's why it's this alternative and why we have this test statistic that is essentially calculating like how much of a difference is there for us to then have evidence to reject this null hypothesis of saying there is no difference.
Okay. Okay, thank you.
Yeah, that's a really good question to talk through and really think about, because once you have this kind of intuitive understanding of this is what we have to work with when it comes to probability and statistics, and what are we limited to in what we can actually test, but also how we are testing this is creating evidence to find this type of insight to say there is a relationship between store layout and average sales. And that's really what we're calculating based off of the variance. So if there is a difference in monthly sales due to store layout, we would expect that the population means would be different, that there would be variance in the mean average sales.
And one question before we like really start the question. The alpha, that's basically the limit of which past, like if it's 0.06, that means it is too what is the word? Too high for it to be null now. At that point, that means it's too big of a difference between the spaces, between the means, I should say.
Can you repeat that, please?
So the significance test percent at level is 5%. So that makes the alpha 0.05, right?
Yes.
So if we get a significance level or the mean higher than that, that means that the difference between the mean is higher than that, and that means that it is no longer the null, it is the alternative.
I like what you're saying. It's the opposite though. If the value that we find is smaller than this threshold, then we would have evidence to reject the null hypothesis. And I'm just going to draw this on the screen just because I think it's always helpful to think about what it is that we're actually calculating here and what that 95 or 5% is really getting at. So just if this was like a one-way type of hypothesis test and we're trying to test if the value is greater, let's say the mean in this sample is greater than the mean in that sample, and we want just to see how significant is it. The 5% is saying like the mean is so far from the expected value that it's in this zone. And that 5% is just this threshold cutoff. So we want our p-value to be in this highlighted zone because it is even smaller than this threshold. Because if we get anything over here, that's essentially just normal because it's so close to what we would expect to see.
Okay, that makes sense.
Yeah, so I think just why I like to draw it is because we're still talking about probability here. And that's what that p-value is saying, is like, to what degree is this significantly different that we would only, what are the chances we're seeing this just due to random odds? And because it's so far out here, there's a really small chance that it's just due to random chance. So that's why we found something, and it's so different from what we'd expect that it's statistically significant at the 5% level.
All right, I got it.
Okay, perfect. And it could be helpful even to review some of those steps when we were first introducing hypothesis testing. If it's, you know, it's always helpful just to continue to repeat those things though. Any other questions before we dive into the problem? Okay. I think some of the things we just talked about will also be demonstrated through this as well. So I am just reading in the Excel file where I have the sheet name here for the store layout, just based off of the question. I think it's always helpful just to see the head of a data frame, just to know what the column names are, what the index is, you know, what are we working with here? I see numeric data for 3 different layouts, and I want to know how many observations are there. So this looks like there's 10 rows. So we have these 10 samples for the 3 different store layouts. So we see 3 columns, 10 rows. And so just from what I have been saying, like, I always like to visualize these things just to see what they look like. And we see layout 1, layout 2, layout 3. And if this was a homework, I would expect, and the final, if there are any graphics that you make, you must have these title, the axes labels, and a little caption. What we see. And we already talked through this, so I won't belabor it too much. So let's talk through how we have this between group estimate of variance, where we are taking just the sum of each sample. So we have this sum of observations where we're just taking for each column, just add up all the values we see. And we have this sum of observations. And I think these are in millions. So the total of the 3 different layouts is 64 million. And the denominator of this is the length of the data frame. So how many observations times how many samples are there. So that's why in this case, it's 30 from the slides. So we have 10 observations between 3 different layouts. So therefore we take the total, and now we're dividing it by, you know, how many, you know, observations are we really looking at here? And so this is that grand mean. And we now want to compare each of the store layouts means to this grand mean and take that squared difference. So next, I will just calculate the mean of each layout using the function we're familiar with at this point, dot mean, for the 3 different layouts. And I would recommend just checking out a recent thread on Slack where a student asked a question of when would we need to specify a column using this type of syntax compared to something like df dot layout 1. So I'd recommend just checking out that thread, but really the difference is because we have a space in the terms compared to if the column was just 1 word, we wouldn't need to use this column where we have quotes around it. So I would recommend, if this is something that is interesting to you or that you haven't come across yet before in your trials and tribulations with this, it's good just to understand a little bit why we would have to specify it this way. And next, I just created a pretty simple function that just takes the number of observations and multiplies the group mean minus the grand mean and takes the square of it and returns that group difference. So not to jump around a little bit too much, but this is just taking this step in the formula and we'll apply it for each of the sample groups. So now that we have this function, I'm just going to run it on each of the samples that we created where we are inputting the group mean of, layout 1, which I defined here. And I take that grand mean, which we calculate in that first step. And then the number of observations is just, again, the length of the data frame. So there were 10, observations for each category. And because I have this function that we defined, we now have this little tool we built and we can use it for the sample in 2 and in the sample in 3 and just change this input for the first group mean. So we're using this function that just takes this squared difference and running it on each of our 3 samples and adding that together to get this sum of squares value. And then lastly, we divide the sum of squares from the degrees of freedom, which would be the number of columns we have. So how many categories are we taking? -1. So, and I'm using, the data frame itself to define these things, but you could also just look at it, interpret it, and understand, hey, we're comparing 3 different layouts. So we would just take 3 and -1 to get the degrees of freedom. And just to repeat, all of this could be done on paper using a calculator. We're just using Python to build these different components together for us to use. So you don't need to do anything manually. And then we'll also show how there's a package that does this for us. So we're just breaking down the function into the different components and getting this mean variance between group estimate. And it's just referred to as this mean. Actually, I should get the actual acronym of what this stands for. But whenever we're talking about MSTR, we're referring to this between group estimate of variance. And so we have this value, and I just posed this question of, is this value large enough to indicate that the population means differ? We would compare this to the variability we can expect due to random chance. And next we need to compare how much variance exists between the groups of the variance just within a group to know this. So now we have this within group estimate of variance, or where we use the mean squared error. We have this degree of freedom. And so, David, this gets to your question of where did I get those numbers from? We just took the variance of each of the store layouts. And that's where those numbers came from. And next, we are just calculating the sum of squared error. Appreciate the thumbs up there, where I can go back and add a little bit more. I think it would be better to have more documentation of what this function is actually doing, because I just assume based off the name of it, you might have an inkling of what it is, but it's much better to just be explicit with, inputs of function, output, what does this function do? So this is called a doc string, so that anyone else who uses your function, knows how to work with it. So I'll go back and add a little bit more documentation here, but pretty much this is just calculating that sum of squares error for each observation. So using now this sample variance between the different groups, we are now taking the number of observations minus subtracting 1, and then multiplying it by the sample variance to get this sum of squared error. And I'm seeing this name error because I didn't hit run here to define that function. So it has no idea what I'm referring to with this calc SSE until I say, hey, I defined this for you right up here, and now I want to use it. So I'm just going to run that again, because now I just didn't hit run in that cell. So now we have this value of sum of squared error. But we have one more step where we need to divide this by the degrees of freedom. which was defined by the length of the data frame multiplied by how many categories we're comparing minus the how many columns, how many categories are we working with? So that's what this, degrees of freedom that we have here. And all of this is defined in the textbook if you wanted to refer to it there as well. So the last thing to do is just put this all together to get our test statistic, where we're really trying to measure if the ratio between group variance versus the within group variance is significantly greater than 1, because that would give us evidence to reject the null hypothesis. Because this is similar to where we have that proportion of like what we just talked about in the last module of with the F test of are these variances different from each other, where, if you take 100 divided by 100, you'll get close to 1, which would say these means are the same. And, the farther away we are from 1 would assume a greater degree of difference. So just defining what our degrees of freedom are from the mean squared error we defined here. So that was from this point. And then we take how many columns we are working with minus 1 for the degrees of freedom for the MSTR. And so here's really our test statistic of this value. And now to create a p-value from it, from using our cumulative density function to know like how far away from the expected value would we be given the degrees of freedom in the numerator and denominator. And that's why we have these different inputs here. And we subtracted from 1 because of just how this function works, because this is giving you everything up into that point, and we want everything on the other side. So this is our p-value. And we would compare this to our alpha. So we would say, let's just define this as p-value, because this is how I've been usually structuring these things, especially in the homework solutions. And this gets back down into your question. So really, we're really just trying to see, is the p-value lower than our alpha? Oops. And if so, so I'm just going to use an if function. So if our p-value that we defined here, which is the probability of seeing this value of our F from the F distribution is as extreme as it could be, that it would pass this threshold of 95% or 5% in the confidence interval. So if our value is farther away, so it's in that little portion when I drew that distribution, then we would have, well, let me do this in the way that we've been seeing it. So if the p-value is greater than that, then we would fail to reject the null hypothesis. Else we have evidence to support the so I should have printed out what I want to have it at, because our p-value, let's get our value of alpha, because this should have gone to the other one. Okay, and I will go back to what I have here for why this isn't working. Because pretty much we just want to compare this here. Let me just make it so this works. So if this is less than, we would expect to see that. So I'm not too sure why this isn't working for me right now, but it's really not too important, because really we're just trying to compare the differences here. So you can intuitively just say if that is lower than alpha. I was just trying to, use Python to show that. So where this would fall in that second one, where we would have evidence to reject the null hypothesis.
You have to put print in there.
Excellent. Thank you. Nice. That's a very good point. There we go. Thank you. That's why, none of us is as smart as all of us.
Extra points for him.
Yes. Awesome. Okay, and so, without going through all those steps, we can use this Python package to create just a one-way where all we need to do is put in the layouts for the 3 different categories, and this will calculate it all for us. So it got us that statistic, and it also calculated that p-value. And if this was a homework question, actually for the homework in this case, I have one question where you need to do it in this manual way. And then the second one, you can just use this package. And it's just really important that you understand how to interpret this p-value and how this relates to the statistic that it calculated. So now that we went through all of that laborious processes, we can actually just replace that all with one line of code and get that same output. Any questions?
So basically, it was null because it was lower. I mean, I know it was rejected because the value ended up being lower than 0.5, right?
Yeah,
Or
exactly. So even
0.05.
just to draw it one more time, we found that's why I think it's interesting that we have this. We're using this cumulative density function to pretty much give us that value from the F distribution based off of the test statistic we found to say how far away is it. So we had our threshold of 0.05. So just the area under the curve just left us this little bit of the area in the tail. And our value was even smaller, where this would have passed an even higher threshold, even above 0.90. So the value we found was all the way over here, so that we have this evidence to conclude that the means of the store sales were statistically significantly different at this level of significance. So if we were to run this experiment 100 times, what's the probability, just due to chance, that we found a value at least as extreme as the value we're seeing? And that value would be very low. So if this was a 99% confidence interval, we ran this 100 times and just 1 out of the 100, we would expect to see this type of value, but we're seeing it. So therefore, it's likely that it's not just due to chance.
Perfect.
And so that's how, this is all coming back together. I do find that sometimes students might find this confusing because we're talking about lots of different things, but they're all pretty related to each other, kind of in the fundamental sense. So I'd say it's okay if this all feels like so many different things that we're doing, but I just would encourage you to think about how they're all somewhat similar to each other. So we will now jump back to the lecture slides. And I think now that we've kind of established this understanding, we might move a little faster through the rest of this, because once we have this just core foundation, the rest of ANOVA that we'll be talking through will be somewhat similar. So we now know from this one-way ANOVA test to see if the means are different. And I mentioned that this is like a zero-sum game. Even if one of the store layouts was different and the other 2 were not, given that test statistic we found, we really have no way of knowing, what's going on and which mean differed the most from the other. So that brings us to these other approaches that were developed that would give us that insight into the direction and statistical significance between the paired population means and construct confidence intervals where we actually do this pairwise difference comparison. So I kind of, we're building up to this where we first just do the zero sum, and now we have a little bit more sophisticated tools to do pairwise comparisons. So this was created, Fisher has this LSD for least significant difference method. And this was later improved upon by John Tukey with this honestly significant difference method, or this HSD. So you just see the time difference between 1935, we have Fisher, and bringing that to 1977, where we have Tukey's test. And it's really important to note that we would only even want to use these methods if we first found from the ANOVA one-way test that we can reject the null hypothesis that the means are not equal. So had that last experiment resulted in a test statistic that was greater than our alpha, where we didn't really find a statistically significant difference in the means, it would be a moot point to even try to test like how are the means different. So it's nice that we have this one tool. It's kind of a very blunt tool that just gets us a step closer. And then this would be a more dexterous tool that can explore whatever we found from that first layer to understand it a little bit better. And I bring up this box plot to just show how we can now start to analyze the variance within each group. And using these types of tools really are now creating this pairwise comparison between them. So just bringing it back to how we can use visualizations to inform our understanding of really what's going on here, where now using a box plot, we can see the means very clearly, but then also the distribution and dispersion of the quantiles and even like these outliers that we might expect to see, and how that might skew the variance within the different groups. So next we'll just be talking about how to calculate these things. So talking about this LSD approach where Fisher replaced the t-test confidence interval for testing the difference between two population means, where now he created this pooled estimate of the population variance, where this is now substituting the mean squared error with the population variance. And this is valid because it uses all the samples to calculate this pairwise comparison compared to only looking at two samples. So we took this t-test and just expanded the generalizability of it to now look at more than two samples. So just by changing the mean squared error using the population variance, this is the key difference here. And we still would apply the t-distribution when we use the degrees of freedom corresponding to the mean squared error, which is the number of observations minus the number of groups. So really just at a high level, it's good to know how we got here to how this is just slightly different. And the way we apply this is how we will now look at the differences as like this pairwise comparison between the different means. So we take the difference between each group to compare pairwise, and we see if the confidence interval contains the value 0. If it does, we fail to reject the null hypothesis and cannot conclude that the mean differ between groups. And one thing to note is that as we compare more means, the likelihood of a type 1 error, which just to remind us, that's when a false positive where we say, hey, there is a significant difference between these groups when there actually isn't. The chances of having a type 1 error increase the more comparisons we're making, because we're splitting things up more between these different individual tests. So just the chances of a false positive on at least one of these individual tests actually just increases, whereas the Tukey method avoids this problem. So at a high level, what we're doing here is taking the t-test and the confidence intervals and now applying it to how we can understand the differences between the different groups. And this uses the t distribution from back when we had students t, from the distribution, which has these broader, flatter tails. And given the probability under the right tail of the distribution, we see this slightly a larger range using the studentized range. And this helps to decrease the likelihood. Oh, I think I needed to also just emphasize this is moving on to another concept where we just touched upon how to calculate. I thought this was bringing us together. This is now showing how this is slightly different, where this is now two keys, significance difference, which overcomes that problem of the type 1 error. And the key difference here is because of using a studentized range distribution compared to the t distribution. And this is decreasing the likelihood of a false positive, really just because we're using a different distribution with a longer right tail. And we're talking a little bit now about how balanced are the different categories. So if we had 10 samples from one store, but 20 samples from another, where there's actually a different imbalance of our data, this starts to take that more into consideration because we want to know how the different number of observations compare to each other. And so if we had 10 times the observations for one class compared to another, we would consider the data to be unbalanced. And actually, this is pretty prevalent in the real world, where you might actually have really imbalanced data. I see this a lot in my work when we deal with high-risk situations. We're trying to prevent an accident from happening. And realistically, accidents don't occur too often. So we're trying to train a model on something that has very few observations compared to the population. So let's just say, like, if you have 100,000 projects, only a very small portion of those will actually have a damage occur. And we're trying to predict that probability of a damage occurring. So we have very unbalanced data where most of our observations are saying, hey, there's no damage that's likely to occur, because most of the time no damage does occur, on the off chance that this is a high risk project and a damage does occur. That doesn't happen too often. So just talking about how when this relates back to real life and we might be trying to model more complex things compared to something that's a little bit more structured, like this store layout problem, we might not really be able to have a balanced type of observation sampling to look at. So I just wanted to bring how this might relate to the real world and how we want to use these types of techniques to actually still be able to measure what it is we're looking at, even if there is a difference in the number of observations between the different categories. So any questions on this? We will be walking through the demo that calculates these things, but really just at a high level, it's good just to understand we can use these two different approaches to actually understand which means differ. So I think at this point, as long as that is the understanding, then we can continue moving forward. But any questions at a high level, but I think they'll be better answered once we finish going through an example.
Which method do you prefer?
I think it depends on the data at hand too, and kind of what the problem is you're solving. So and also it kind of, again, depends on what your approach is. If you're using a statistical model compared to something like machine learning, which takes different approaches. So what we've been covering in this class is more about probabilities, So it's more statistical model. And I'd say at work, on my team, on the machine learning team, we do more with kind of data-driven types of models. So in short, I guess if I had to give what I would say is my preferred approach, we should likely start with that one-way ANOVA and see how that goes. You kind of always want to work with like the simplest thing first and then build upon that to get you to where you want to go. Kind of getting back even just to module 1 where we had Occam's razor principle of you want to start with the most simple model and then build and add more complexity onto it. So I would start with a one-way analysis of the ANOVA, see, hey, do the means differ between these two different groups? And then if they do, I would suggest using Tukey's over the least significant difference approach because it has this larger tail that would minimize the likelihood of a type 1 error of a false positive.
Okay.
But I appreciate that type of question because I think it's important. Like, how does this relate back to how you might use this in your job? Because you can definitely start applying these types of things, even just to understand, the difference in like A/B sampling between two different groups. But any other questions? Because next we'll be getting into this two-way ANOVA, but maybe let me just quickly check for the demo because maybe this would be a better time to walk through these things. And I think I'm just going to look ahead a little bit because we'll be getting into this two-way ANOVA test. So yes, let's walk through quickly how we would calculate some of these things from the using Fisher's least significance difference methods and then using Tukey's. So from that same case study where we have the store layout, we are now taking a pairwise comparison. So instead of having our null hypothesis be that all the means are equal to each other, we're now relaying back to our t-tests where we're just comparing, does the mean from one group differ enough from the other, where we would see it equal 0. So we are now just comparing, does the mean from sample 2 differ from sample 1? And if they don't differ, then it would equal 0. If you took 100 and subtracted 100, you would get 0. So this is our null hypothesis saying that the means are not different from each other. Or that they're equal to each other, which is equivalent to what I just said. And then our alternative is that not all populations are equal. So this is breaking down that zero-sum game a little bit more because we have this pairwise comparison. And we will define using that same confidence interval of 5%. We have this 95% confidence interval, which again is just the other way of saying at a 5% significance level. And in this case, we have it for two tails because we are just seeing, is it equal to 0 or is it not? We're not saying, the mean in sample 2 is greater than the mean in sample 1. So that's why we would take this area under the curve and divide it by 2 because we want to account for it being farther to the right or to the left. And so we get our critical value of like how many standard deviations away would we need to see for our value to be considered significantly different. So we use that t distribution and we get this percent point function just using the degrees of freedom. So none of this is new because we defined this type of approach when we were just doing the t distribution, getting that critical value. And now we are creating this upper bound and lower bound confidence interval between our two values using this mean squared error and just the number of observations between sample 1 and sample 2. And this is just using the formula that was defined for us in the textbook for how we calculate these differences. And so we are now saying that there is this difference in means from sample 1 to sample 2, where if this interval contains 0, we would fail to reject the null hypothesis because they don't vary enough for us to support the alternative hypothesis. So we would just take this output and compare if 0 falls in between the intervals. So the exact same thing we did when we had the t-tests. So in this case, the difference between the first two means, you can just intuitively see one is negative, one is positive. So therefore 0 would fall between. So we cannot conclude that the mean monthly sales differ between layout 1 and layout 2. But if we were to look between 1 and 3, we see these both fall on the negative side. So 0 is not in between. So this is actually, this test gave us evidence to reject the null hypothesis that the mean difference between layout 1 and layout 2 and layout 3 are statistically significantly different. And then the same thing for 2 and 3 because 0 doesn't fall in between. And this gets us back to what we first saw, which I guess I kind of blew the surprise when I was just visually looking at it, because we kind of saw this difference in layout 3 being pretty different from layout 1 and 2. But now using this test, which again is just using the t-test and applying it in more than one group, we can now say with statistics that layout 1 and layout 2 means are very similar to each other, where we can't say they're statistically different, but layout 2 and layout 3 are statistically significant enough at this threshold of 95% confidence interval that the store monthly sales are different. So if you had to present this to your manager, you could say layout 3 resulted in statistically significant difference in monthly sales, and it looks like it actually increased monthly sales. So therefore, you can make more money and keep layout 3, if that was going to be like the outcome of whatever you might suggest. Or maybe there's more research to do, and maybe you want to continue improving layout 3 and keep testing it. And next, I will just walk through how we do a very similar type of approach, just using Tukey's method, which was, again, pretty similar, but it just is more robust to type 1 errors, where we would have a false positive. So maybe, this could be a false positive of saying layout 3 is statistically significantly different, where perhaps we would want to just take more samples to reduce that likelihood of a false positive. So in this case, we just have to structure the problem a little differently in order to use this package. So I am just going to walk through how I use this melt function, which, if anyone's familiar with Excel, is essentially just creates like a pivot table, and it unpivots things. So you can see, for each layout, what is the value. So once I put this onto GitHub, I would just recommend playing around with this code, because pretty much I'm just changing the names and just wrangling this data frame a little bit so that we have the different layouts that we want. So just by doing this, now I could more easily create a box plot. And I added this swarm plot onto it. I'm just kind of curious what happens if I do this, because it seems like these two things. Okay, so the swarm plot creates these different points along it that just gives a different distribution of the values. So this is just showing the different observations and how they vary from each other just on top of the box plot that we're familiar with. So it's just another way of visualizing the distribution using these points. And we see how we talked through this, where layout 3 again seems to consistently deliver higher monthly sales where there isn't a lot of variance between the sample. And so now I'm just stacking this, and maybe this could be a little bit more clean for how we would want to get here. Because pretty much I'm just getting us to this point where we can use this Python package for pairwise results that takes these different values and we'll calculate it. And I think I would just recommend reading this a little bit more for more documentation if you're curious, more of the context around it. But just for now, just knowing like how to do it and how to interpret it, we're essentially finding a very similar thing. And now this just creates it does actually a lot of the heavy lifting for us, where it even tells you if you can reject or fail to reject the null hypothesis. So between layout 1 and layout 2, it creates this mean difference. It calculates that p-value for us. It gives us those confidence intervals. And even you don't need to think, hey, does 0 fall between these intervals of lower and upper? Because it'll tell it for you and say false. We can't assume there's a difference between layout 1 and layout 2. That's why it's important to understand just how to interpret these things. But between layout 1 and layout 3, there is a difference, and layout 2 and layout 3, there is also a difference. And by default, it uses this alpha of 0.5. But if we wanted to change this, to something even less, let's see how that would change it. So to that degree, we couldn't. Let's see, even at this, if that would change it. So as we change, like how statistically significant we want our threshold to be, we could, it's kind of interesting to see layout 1 and layout 3 actually would still pass our threshold to say layout 1 and 3 are the most different, where maybe 2 and 3, there is still some, it's not as different as layout 1 and layout 3, just from looking at this type of thing. But we would want to probably investigate a little further before we would make that type of conclusion. But pretty much this is getting us a little bit closer to what we want to know to understand. And I just added this ordinary least squares model, because if we were getting into regression, this is just a little sneak peek into that, which in our class we won't be, but I assume in the next class, hopefully that is where you're going, where we are now really ready to start creating models to try to predict, what the mean sales might be based off of the layout. So this is just showing how we are really at this point where we can start to use the value of the mean sales as it relates to this categorical variable of layout to try to understand the statistical relationship between these different values. So this is just another way to get this ANOVA output to see these different values of the F. So this is really just showing you, hey, there's lots of different ways we can calculate the same thing and get at what we're getting at. And one last thing to show in this, because this will help us once we get to the two-way ANOVA, where I found this other package that's pretty helpful, that does a lot of the heavy lifting for us, which we have up here, called BioInfoKit. Where actually a lot of this stuff started in agriculture and like bioinformatics, and now we just apply it to lots of other things. So I'm just going to use that package, which didn't come pre-installed in our Colab cloud environment. So we just need to install it ourselves using this exclamation point and pip install this package so that we can use it. That is similar to when we really started this class and had that Yahoo package where we needed to install it as well. So now that I have this package installed, using this thing just called stat from BioInfoKit, it has this Tukey HSD for us, where again, just knowing like how to put the right things into it, we will have the same type of summary to show us each step of the way. And again, I'm just showing you lots of different ways to answer the same problem. So just showing it, and I would recommend just taking some time to look at these different approaches and get comfortable with one of them and use that for your homework. And one last thing, perhaps this might be related to the next one, where we have these residuals from this output, where this is getting a little bit into other aspects to consider, just when it comes to what are the limitations of what it is that we're doing, where we can start to look at the residuals, which is pretty much how different is the value from what we would expect to see. So this is just creating a probability plot to show the percent of points for a given value, just to see how many of the points fall within the first quantile. So this is just showing us the distribution of values within the ANOVA in order for us to check our assumption that the residuals are normally distributed. So this is so we can validate our assumption that the data was normally distributed so that we can even use the ANOVA. So this is just a little extra context. If we were to apply this in real life, this would be something to consider to make sure we attest our assumption that the data is normally distributed based off of the residuals that we see. So if these lines fell too far from this 45-degree line, we might have more evidence to suggest that, hey, this ANOVA might not have been valid because the data isn't normally distributed enough, because the residuals aren't normally distributed enough. So this is just a good sanity check to do that's a little bit more advanced, but really shows more statistical robustness in whatever it is you're doing. Okay, so now to wrap up our class with the two-way ANOVA testing, where now we'll extend this analysis to look at more than just one factor, such as the wheelchair manufacturer and the type of tire used, where we first just looking into this one way of one effect in isolation of the category, and now we are looking into the effect of one factor while controlling for the other. And our goal is to find the model that best explains the unexplained variance. Or this is really thinking about that sum of squares error and trying to minimize that for the F-test statistic. So we're trying to minimize this unexplained variance due to just chance by explaining it through the variance between different samples. So beyond knowing how one factor might affect the outcome of the dependent variable, we can also test the interaction between the factors, such as considering if having air-filled tires creates a difference between the different wheelchair categories. We have a test to determine whether these factors interact. So perhaps having one category over another of wheelchair isn't enough to actually have a significant difference. But when we look at this other category of are the tires solid or are they air-filled, we really start to understand the insight that we can really gather from our analysis. Just to compare what is really changing here, for one-way ANOVA, we state the null and alternative hypothesis. And I showed how in Python we can use this F statistic and the p-value to test if we can accept or reject the null hypothesis. But thinking to the problem, we cannot assume that annual income can be determined from industry alone. So going back to that, I think this is a different example. that we'll be getting into. So this might be jumping ahead a little bit when we want to walk through the demo of another case study where we want to test if the average income for 3 different industry types are equal, where we would use this type of approach to test if they are different. We cannot assume that just from industry experience, the industry itself is the key difference. We might want to look at the education level or years of experience. This would be a good time to then use two-way ANOVA test. So I think I'm jumping ahead. So let me just reference back to the demo because I think there's a little context here that we're missing, where we probably should have talked about this first before going to that slide. So let me just bring this in, where we're now talking about this two-way ANOVA test, where we are simultaneously examining the effect of 2 factors on the population mean. So this is that example where I was talking about, where we have different income levels for 3 different industry types of educational services, financial services, and medical services. And we want to see if there is a difference in how much you might earn for these different groups. So now I'm just using our stats package rather than walking through all the steps. And so just from this F one-way test, we have a p-value that is much greater than our threshold of 0.05. So we don't have any evidence to reject the mean to say that someone in educational services would have, a higher income than someone in financial services based off of what we found here. And this is just to demonstrate how we would want to now think about something else that might be proving this. So this is just showing what I just shared in that slide of how we can use these types of approaches that we just learned to create our ANOVA test to see if there is a difference. And there is not. And perhaps now we need to think about another factor to consider. If we're really, if we have this hypothesis and a subject matter expert was giving us insight to say, hey, I think educational services, it kind of actually depends on like how much experience or another factor, and we should explore this further. So now this is another data frame that gives us the same 3 categories. But now your SME or the subject matter expert is like, actually, it's more about like how much experience this person has within the different fields that would really give a difference in their average salary. So this is now adding the second factor we're going to look at of their high school, no high school, bachelor's or master's degree. And this is me just wrangling the data in another way to get us in this value so that we can use our box plot. So again, I'd recommend just playing around with this code to really understand how this melts thing is creating a pivot table. And that gets us into these distributions of means. And actually, even just looking at without the category of which industry they're in, we can see someone with a master's degree has a higher value of this income compared to someone with no high school degree. And we really see these stark differences. And using the box plot actually now shows us the variance that might exist, where the average for masters, let's say that's around 90, but it could go to 110 or even below 80. So just seeing the power of our visualizations to start to understand what we might expect to see, where when we just looked at the mean value, just using the industry, we see the means are somewhat similar and the dispersion of data is pretty similar. But when we now take these 2 confounding factors, we will need to see what happens next. So next we'll take the mean for each of the different groups and the mean for the education levels. And soon I'll talk through on the slides. So this might be jumping ahead a little bit of how we calculate these things. But again, this is pretty similar to what we did in the one way. We're now just looking at different interactions. So I'll keep walking through this and then I'll go back to the slide deck to talk at a high level what the steps are, mostly just for time sake. We create this grand mean. We have the number of groups that we're trying to compare. So now we have 4 groups compared to when we were just looking at 3 categories. We have our squared difference of what we're trying to calculate between. And we are going to just apply the steps that I'll walk through shortly to this other type of two-way analysis. We are taking the same type of approach of seeing how much does the industry change. And now when we add this other factor of their, education level as our factor B, we're now starting to see how that affects it. So we're taking each of these different categories and looking at it on its own, like without interaction between the two, because we're looking at just how does education affect your average income and how does your industry affect your average income as 2 separate things. So that's what I just talked through right now. And now we are using this total sum of squares to just now calculate how different are these things. And we have this value of our sum of squared error. And how to interpret this: when we used one factor to explain the average incomes, say the industry of employment, we see the sum of squared error was 7,902. By ignoring the second factor, which was education level, we didn't see a significant difference by field of employment. But when we do include the second factor, our sum of squared error is 269. Let's see if that's, I think some of this is a little disjointed. And I think when we go back to the slides, we'll have some more of that context here. Where we want to bring this all together. Okay, here's where that value is. When we include both education and industry, and we wanted to compare the mean income between the different industries, our sum of squared error now decreased. So we're better finding the average income when we have these 2 categorical variables together. And this is an example of our 2-way with interaction type of ANOVA test. And I know I went through that pretty quick, but mostly because we'll talk through those steps in the slide deck, and perhaps a textbook is also a good way to have a better step-by-step approach. But it's also very similar to what we just did for the one-way ANOVA, where now we're just introducing this interaction between 2 categories and seeing how that relates to the variance between and within the different groups. And so now we can even apply using our 2-key test to start to see this same type of pattern between group 1 and group 2. And now we're combining that with all the different combinations. So we're creating the combinations of different categories and seeing what that statistic would look like of this variance. And it's doing all of the heavy lifting for us using these packages, where now we have the results to say the difference between masters and bachelors in this case would have a statistically significant difference compared to bachelors in high school. Actually, from this sample, there isn't, because we see this value where we can reject the null hypothesis. And we can start to really understand the differences, but now if we have this pairwise, where we are looking at just the two different groups, we have there is no statistically significant difference just between the different financial services compared to educational services. And just to keep walking through this so we can get to the end here, I'm going to show what this would look like with interaction, and then we'll finish up with the slides. And I would say there's probably more to talk through in some of these when it comes to the math behind it. And we'll have a lot of that with how to calculate in these steps. So I would say for the homework, walk through these different steps. And it's all pretty similar between the one-way and the two-way of what steps we're really taking here. And we're essentially doing a very similar thing. We're just now comparing it between groups. And we have the same type of test statistic. And I'm just going to touch upon this before we get into the with interaction, where we're looking at the rows to see how much variation exists between the rows, between the columns, what's the error overall, and then what's the total error. And when I say this error is because we're trying to better fit the probability of income based off of the categories that we're exploring. So that was, for example, the category of just your industry type doesn't have a high relationship with your income. But when we added this second category of your education level, had a higher relationship. And next we'll talk about how when they interact together, where not just your education on its own, but your education plus your industry, that's when we'll start to see the largest effect. So let me just walk through this probably a little faster than I'd like to if we had infinite time, but just for the sake of demonstration how these things work, where I'm taking a similar approach of creating like a pivot table. So we just have every combination between the education and the industry. And now we have the same type of breakdown. And this is now taking the mean between the groups. So now, rather than the mean on its own for each of these different categories, now we're taking the mean of every sample in the education industry that has a bachelor's degree, that has a high school degree, that has a master's degree, and a no high school degree. Which I guess I shouldn't say that, where they don't have a degree, where they didn't go to high school, how these different means of their income vary. So we're just taking the average between these different groups. So you can even see, someone who has no high school degree, how there's just slight differences between the industries, whereas someone who has a master's, we just see the differences between medical masters compared to educational with masters. And we can then start to just see the difference between, having a bachelor's compared to having a master's for educational sector. So that's what this code is doing, is creating the mean between these different combinations that might exist. And we use these different factors to create the inputs for our ANOVA, our two-way ANOVA test. So this is pretty similar to the one-way ANOVA, where we're just calculating the differences. And again, I just say play around with this code, see what's going on under the hood, and follow up with any questions on Slack that you might have. I'd be happy to walk through more of these steps if you have more questions of what's going on here. Because we're using the same exact functions that I defined just for the one way, and we're just using it in another way for these two categories. We're looking at the sum of squares for each factor. And we're just applying the steps that are outlined in the textbook and in my slide deck. But again, I would say just read through the textbook to have more context around what's going on, because I'm just going through this pretty quickly to get all the different inputs for this function. Where we have that same table, and now we are just calculating this interaction between the two different groups. So this is just creating all the different inputs for us to do the same exact thing that this table does for us, where it's just trying to find the mean of one value given this combination. And this is just more code to get us to the same point of what I'll show at the end, where we have a package that does this all for us, but just to better explain what's going on in the black box of the package that I'll show you right here. This is just how we would get there very manually. So next I will just show how we would do all of that steps that I just quickly breezed through as a package here, where all we would need to define are, we're looking at this category of industry and we're looking at this category of education, but now we're adding this interaction between industry and education as our last factor here. And we are now able to see how we would interpret this value, where we are trying to analyze this sum of squares difference for the groups. When we use the box plots to show some of these differences, and we saw that the sum of square difference between education groups is much wider than when we just looked at the industries. And the interaction then between groups showed a tighter variance, which can help inform our interpretation of how these factors might be used to predict the likely income. And this F statistic here is used to measure the variation between the sample means and variation within the samples. So the variation between education levels versus income is a lot more varied compared to the interaction between education versus industry. And we start to see some of that when we look at this table that gives us some of these statistics. And lastly, I want to just talk about this pretty key caveat when we are talking about this ANOVA framing. When we have interaction between things, that's called Simpson's paradox, which is defined as any trend seen in aggregate data that could be reversed if we were to split the data into different groups. So this little video here of different groups is an example that tested a news report that eating pasta would help someone lose weight. And this just shows when looking all together, the trend shows that people with higher BMI eat more pasta. And then if we were to actually look at different groups within this, we would see that each color category that are green are people with different BMI levels, where we actually, if we were to break this larger trend into different groups, we could make some type of insight that actually isn't really representative of the larger trend. So just in short, this Simpson's paradox, I would recommend reading this link of this case study that does a really good job of demonstrating this type of statistical quirk that could actually really be exploited to try to make whatever case it is you're trying to prove, where just by breaking up the data in different categories, we might be able to find different trends that actually don't represent the larger group. So it's important to be critical of how our statistics can be interpreted and make sure the conclusions that are drawn are carefully considered. So just in general, this Simpson's paradox is good to think about when it comes to, are we fairly aggregating the data in a way that makes sense? Or are we stratifying things in a way that might reverse the trend that we would expect to really see if we were being more true to the data itself? So I jumped around a little bit here because this now walks through all of the steps for how we would calculate this with interaction step. So I brought up this Simpson's paradox because we're essentially looking at how different ways you break out the large population into groups. You have different interactions that might exist. And we use this two-way ANOVA test with interaction to capture these possible relationships between the different factors. So we are exploring if the relationship between education and field employment is something that would be statistically significant. And we want to see if it's this interaction that's really driving it, or is it each factor on its own? So with that, I know we went a little quick towards the end to just get through these different steps for calculating the two-way ANOVA analysis without interaction, when we just looked at these different categories on its own, and then with interaction. And I will provide more steps on Slack if there are confusion about how we would tackle these different steps. And the demo in Python also walks through each step. So I would recommend using the textbook to look at each step and then going along with the demo for how to calculate this in the homework. And follow up on Slack if there are any questions to consider. Because in this module, we really covered a lot, which I think if we had more time, I would want to break this into 2 classes where we just talk about analysis of variance with one way, and then we spend the second class talking about with two-way and this interaction, because I think there's a lot more to talk about when it comes to doing these two-way analysis of variance, because it really gets into some useful tools for how we see the different patterns that exist in our data as it relates to what insight can be created from our experiments. So with that, I will end the presentation and stop the recording.